attract more interesting for this working group and may get ready, when we come to the point we may recharter. So we will have, try to run such wide discussion sessions for even the following IETF meetings to be, ready to what we may be interesting as a working group for next charter. This is the note well. Everybody should already see it so many times, but still you need to know almost everything on it. We already give out the 2 blue sheets. Make sure you signed before you leave, if you want to leave earlier. And we still want the job scriber and minutes taker. Anyone volunteer? No. Anybody volunteer?
Can I get you to?
No. We need at least minutes taker to run the meeting.
So people who got themselves a table are ideal candidates. Eric, can you? No?
Lauren? I mean, I know you make presentations, but could you do the minutes take when you're not present? And Bing, could you be the backup? Thank you. Okay, let's get out the meeting agenda. This agenda is slightly changed from Tuesday, what we showed Tuesday, because Rene is decided to postpone his presentation. So we actually get another 15 minutes, and we reassign most of time to reference module, which is the milestone work item, but not in very urgent, maybe next meeting or the meeting after next. So reference module gets 30 minutes, and coordination multiple autonomic functions and Norrent for 50 minutes, and self-managed network with fault management hierarchy. Tony is here? Oh yeah, sure. And predictive risk awareness for proactive management. And at the end, we have 15 minutes closing to give some ideas how the chairs want to, organize the work items and to move forward from this meeting to, between this meeting and the next meeting. We are expecting, people to and also attend the interim meetings and make progress there. Thank you. Any agenda bash? Okay. Michael?
Thanks. So this is
No. Maybe I switch there. Yeah.
That's better. Test. Works now?
Yeah, works. You may write it.
More or less anyway. Okay, thanks for your interest. This is about the reference model. Go straight to the next slide, please. This is a slide from last time, just setting a little bit the stage where we are and what the background of this is. This has been around for a while in a conceptual state. Now we are getting to the more concrete state. The goal of this document is to define how the various elements in an autonomic network context work together to describe the interfaces and relations. So one step back, we are now, if you're on the mailing list, there are discussions about the signaling protocol, the autonomic control plane, and all sorts of bits and pieces. What is at this point not clear to many is how this all fits together. And the way to run this is basically look at it from a requirements perspective. Right? What are the requirements on those protocols? And this document with a sort of a reference model tries to show how all these various components fit together. With that, we hope to get a proper understanding of what is required from all these various components, which value they add, so that we can make an overall clean picture. Okay? Next slide, please. So, this is sort of a functional model. The yellow boxes that are pretty big, they represent a node. So this is a network with 5 nodes here. And the first observation is what we are defining at this moment in the IETF, in the Anima working group, is all primarily the autonomic networking infrastructure. These are services that are provided to what we call autonomic service agents. The next slide will make this clear, but let's stay here for a second. Not everybody will have been in previous discussions. Let me just recap from last time. The autonomic is not really new. There are a number of autonomic functions already, such as OSPF, you could say, is a more or less autonomic protocol. It talks to neighbors, and routers figure out on their own what they need to do. That is sort of an autonomic function, right? But all those autonomic functions that exist today are completely independent of each other. So if you have an OSPF process and an LDP process and a BGP process, they all do their own signaling, their own messaging, their own security, their own everything. That is expensive from an implementation point of view, but it is even more expensive from an operator point of view because, for example, from a security angle, every autonomic function needs to be secured on its own. So you have security for OSPF, you have security for BGP, you have security for LDP, all of which is relatively complicated. So the idea of the autonomic networking infrastructure, and this is what we are talking about here in Anima with the current milestones, is to create the infrastructure. And so for this to work, every node has to have sort of a minimal set of features so that the autonomic service agents, which will pop up in a minute on top of this red line, can use them. So at the bottom, we used to call this various different things. It used to be called a vendor ID. Then somebody said it should be called a manufacturer ID. Actually, right now because I didn't like either of them, I just call it a preset ID. So a device comes with something preset. That is what we are trying to drive towards, is this 802.1 AR device credential, a certificate built into the hardware that would provide you the optimum security. And that's that. In a lesser secure case, you have a serial number there, for example, but something that the device comes with when you buy it. Then there is draft predicate, bootstrapping, key infrastructures. That illustrates how you take a preset ID, which is not specific to your network, it is a generic thing for all devices that are out there, and convert that, quote unquote, derive from it, is better said, a domain identity, such that now the devices can actually talk to each other and say, I am this device at domain X, and the next node says, I'm device Y in the same domain. So now the two devices have a domain identity. They can authenticate each other as belonging to the domain. This is a must-have, right? In one way or another, an autonomic device must be able to assert its identity within a zone of trust. Now, on top of that, we are building what we now call the autonomic networking infrastructure. And these are the discussions that you have seen on the mailing list about GDMP, the bootstrap, the ACP. There has been some discussions about naming, addressing, discovery, and so on, and so on, and so on. These are all functions that the autonomic networking infrastructure provides to service agents which run on top of that. And now the key point of this slide is If we want to have an autonomic networking model, there has to be a must implement part of the infrastructure such that an autonomic service agent knows what it can use and what it can rely on. Right, so the first observation, this is below the red line, is pretty much must implement. Needless to say, there will be revisions, there will be more or less capable nodes even then, but there needs to be some common understanding on that level. One thing that has also become clear, we have been focusing mainly on quote-unquote normal networking devices, say routers and switches. It is also clear if you take the concept, and the concept per se applies everywhere, also in the sensor world, for example. But if you take this, what we are talking about right now, to the sensor world, and if you mention to a sensor person an X509 certificate, his eyes go red and he starts shaking, right? So there are certain things that we cannot do on constrained devices. How this will pan out is not clear yet. In my opinion, we will probably have minimum two, possibly, hopefully not, more variants of the same thing. So there will be a core type of feature set of an autonomic networking infrastructure, and then something that's constrained in one way or another to allow for these devices also to participate. All of that, as you can tell, we are not completely through with defining it, but from a level of thinking. Okay, next slide, Jim. Thanks. So here come the autonomic service agents, ASAs. An autonomic function is something that runs on a network. The OSPF, the overall OSPF process in your network, is an autonomic function. And the function is composed of autonomic service agents on various nodes interacting with each other. That's a pure definition question, but that is how that has been defined in research previously, so we are reusing the same model. So you can see that there may be now an autonomic function that spans the entire network with an autonomic service agent on every device. There may be autonomic functions that span only parts of the devices. Those, by the way, do not have to be adjacent, so it can be anywhere. And actually, if you look at it, if you have followed a little bit the bootstrap discussion, there's this registrar concept. Actually, that is an example of an autonomic service agent. Very specialized one, but it is a service agent that runs on top of the infrastructure. And in fact, also from an implementation point of view, that will be a separate element in the whole chain. Now, those autonomic service agents now use the autonomic networking infrastructure. See this really as base infrastructure providing services upstream. That's really what this is about. Now, the big question, of course, is conceptually clear. Next slide, please, Sheng. What is the interface here? And that is something that we need to work out in more detail. We have sort of high-level some ideas on how this could pan out. The problem here is we can have this interface on various levels, actually. So the most simple level here is in the text box here. The very basic API examples is you have the autonomic networking infrastructure gives you essentially a normal network with a few features. But what it allows you to do is to send a message, send a packet to another node. So in the simplest of all forms, an autonomic service agent is essentially a TCP/IP or whatever socket on a device that talks to another TCP/IP socket on another device, and they do their own thing. In which case, you would benefit from the naming, maybe the addressing, but maybe nothing else. So this is I would call it the lowest common denominator. The autonomic networking infrastructure in that case provides not that much value. Right? It doesn't do much clever stuff, but it is obviously the easiest to support and to implement. So maybe that is the starting point. We have to map all of this out. Next slide, please. So in the basic model then, the ASAs would communicate. Just think normal process talking to another process on another box. And then again, so there are there is the autonomic control plane draft, which you may have seen. In the autonomic control plane draft, you get a separate context, which is secured hop by hop. So you get actually a secure control plane. So if you use that, even if you do nothing else, if you just call another node with its IP address and UDP port, whatever, it still provides value because you actually have a secure channel in between. So security does not have to be done by the ASA. You can assume a secure connection between the two. And yeah, you could take then simple unicast, multicast, whatever, over this infrastructure and use it as a normal side network, virtual network on top of the normal infrastructure. That is one way. One thing that's important to point out, ASAs can also communicate not only between different nodes in all sorts of normal ways, but also on the same node. So we need to foresee that as well. And now this is where the GDMP discussion comes in, where the autonomic control plane discussion comes in, because the autonomic control plane could be this orange bar in the middle that brings everything together. GDMP is the protocol that allows negotiation between those nodes. See how it all comes together here, basically. Right? Next slide. So on an advanced level, it would be nice, wouldn't it, if we'd have nice programmatic APIs for an autonomic service agent to talk to services of the autonomic networking infrastructure. Wouldn't it be nice if you not just send a packet, but you send a message and you say, I want reliable transport of this message. And the message is whichever size you pick it to be, and it's the infrastructure that takes care of transmitting that in the way you have requested it to be transmitted. Parametric negotiation. Wouldn't it be nice if I don't have to invent my own negotiation protocol, but I could just say, here's option 1, 2, 3, negotiate with node X. And the result that comes back, you have settled on option 2. Wouldn't it be nice if you had discovery functions? Where is my registrar? Response comes back from the autonomic infrastructure, it's here. Or where's the closest, or whatever, all these questions. Right? Also think message bus. Tell me about all events that concern call managers. Assume a call manager is an autonomic element. This is sort of publish-subscribe model. Right? So that's another function call in a way that you could have on top of the autonomic networking infrastructure. You see the two models, and that's an open question right now. There is, on the basic model, the advantage that it's very simple to implement, but the value is not that massive. There is value, but it's not massive. On the other hand, you see that it is definitely more complex to implement, but the value could also be much higher, meaning if we are successful with this, in the future it may be really easy to write a distributed network application, because all those functions, find a resource on the network, communicate, negotiate, are all available as APIs. So this could become sort of a higher level networking model, much easier to program, to use. Right? And so we have to find here the right balance, bottom line. Right? What is the right way to do that? Next slide, please. So here's version 0. We tried to do an update before the IETF. Unfortunately, we didn't quite manage that. This is a lot of, looking at the page numbers, you can tell a lot of that is actually not even filled in yet, so a lot of that still needs to be done. There is a network view. How does an autonomic network overall look in a network? What are the elements? The elements are then explained in section 3, the various types of elements. We discuss a naming scheme, an addressing scheme, the trust infrastructure, how the trust works in an autonomic network. Then the autonomic control plane. And again, you have, for many of those, you have different drafts in the end, right? So this is just the thing that holds it all together with all the functions that the control plane has. We need to take care of non-autonomic functions. How do they interact with autonomic ones? And the rest is clear. Clarification, question?
Hi, John Dowdle, Airbus. Can you just go back to the previous slide, please? So, sorry, this is my first time in this working group. I'm a little new here. I'm mostly working in MANE, Mobile Ad Hoc Networks. I are you looking to reuse a lot of the work that other working groups have done and build on it for,
Yes.
looks like more advanced service discovery topics?
So whatever we can steal, we will steal. Shouldn't use that word probably. We are already using concepts from other groups. We are using Ripple, for example, here conceptually. None of this is agreed, right? So the working group needs to go through. But concepts like Ripple, like MDNS, DNS service discovery, all are here. And in an ideal world, we want to use exactly those protocols in this context, basically.
Yeah, so Manet has some concepts for both neighborhood discovery. There's a protocol called DLET, which effectively gets you edge-triggered neighbor discovery because it looks for it looks to inform routers that neighbors have appeared through radios, wireless, things like that.
Would you mind opening up a discuss on that on the mailing list? That
Sure.
sounds interesting.
Yeah.
Thank you very much.
Okay. All right.
That would have been exactly my comment. We do have drafts out for this discovery negotiation and the like. Would be great if you can say for this you actually can leverage something that's already existing. Let me, Hannes, is it a clarification? Now let me just finish. It's 2 more slides and then we can open the general discussion. Next slide. So there are still a lot of things to be addressed. As I said, it's in the early stages. So for example, for the autonomic service agents, what is this API? What does it look like? What should we settle on? And we need to have one view here in this working group and in the IETF on which level we are starting with. And maybe we go higher up later on. All of that needs to be panned out. The idea is, even if there isn't a real API, even if we give TCP sockets down there for now and let those ASAs talk plain TCP IP over the autonomic control plane for now, even then we probably want to have conceptually clear which functions are going to be used over that. So even on a conceptual level, we do want to have an API. The ACP is a new concept. There is a draft on the ACP, on the autonomic control plane, that describes the ACP as an overlay network that is self-managing. In other words, that overlay network creates itself without any need for configuration. And then you run the autonomic functions through that, which gives you security and a context. It gives you naming, addressing, it gives you everything that you need to communicate. Right? So this needs to be described better, how the ASAs will use this autonomic control plane, and if necessary, how they also communicate over the data plane, because both are obviously possible. So some negotiations or some transfers may happen over the data plane, some through the ACP. That has to be conceptually made clear. The management is a complete different story that we need to address. So that includes the creation of intent, not mentioned here yet. That is in the NMRG definitions draft, if you're interested, how this is ingested, how it's propagated. Feedback loops. So there will be, or there is in the autonomic concept, there's the idea that the network can go back to the operator and say, here is a corner condition. What do you want me to do? We have detected the following condition. We suggest to do X, Y, Z. And unless you tell us differently, dear operator, we'll execute this. So there needs to be a feedback loop to the operator or an NMS system. That needs to be described in more detail here. In this document, we don't do protocols, so that's all done by separate drafts. Next slide. Then capabilities between the autonomic service agents. Imagine in a phase 1, we have a very simple autonomic control plane, which is essentially a TCP IP model, socket talking to socket. And imagine that we now build ASAs on that model. And in 2 years' time, we start with really sophisticated ASAs that do much more. Then you probably need to exchange capabilities between ASAs so that they know what they're capable of. Right? That needs to be coming in somewhere. Also on the infrastructure, not explicitly mentioned here, but also on the infrastructure, on the nodes, also there, needless to say, there will be versioning. So also on that level, we do need to have some sort of version control so that devices can construct an autonomic control plane or the infrastructure, even if they are from different background, and one is old, the other one is new. Then Yes, more than one security level, I already mentioned. There are constraint devices that may not be able to do asymmetric crypto, for example, or at least not as often as we foresee it right now. So for those, we likely will need another security level. The same thing for capability level, just in what the node is capable of doing in terms of interactions. So not all nodes may support the full autonomic networking infrastructure with all bells and whistles. We foresee, for example, that there will be edge nodes that, for example, when it comes to routing, only support spoke functionality, not spoke. You know what I mean. Then one question that popped up on the list is discovery and negotiation. Is that one thing? Is that two? Should we have one protocol that does both, as currently planned by GDNP, or would it be better to keep separate? And that is the discussion that we also have to finalize. Obviously, if we have both in one protocol, it can be made more efficient. If we have two different protocols, it is easier to reuse existing components such as DNS service discovery or things like that. So all of that has to be decided. Next slide. So yeah, this is the last slide. What are we missing? Lots, I'm sure. There are still lots that has to be thought about, and we need all your eyes and ears on the overall approach, not just on a single draft, but on the overall approach to make sure that we are not missing something really obvious. It is a fairly complex construct, so we need to make sure we do this well. Contributor list is completely open, so if you want to contribute, just shoot an email, preferably with some text. Next version, so we definitely want to have a next version before the next IETF in the next few weeks, ideally. One request to all potential contributors: let's not make this a 100-page document. Let's keep that as concise as we possibly can. So try to write it in 1 or 2 paragraphs rather than 1 or 2 pages. Try to make it really down to the point. And so finally, we want to adopt this as a working group document. This is a milestone on the Anima Charter, but it's not the first one. Thus, priority is at the moment on negotiation, ACP. Those are the 2 priority items right now, and then the reference model will come. But obviously, we have to do this sort of in parallel to understand what the requirements are on the components. And with that, open for discussion, questions.
We're not going to take discussion here. It's only for clarification questions. We have another 5 minutes. Yeah, only.
Do we not do any discussion here?
Could you do it in 5 minutes?
Sure.
Okay.
We already gave you 10 more minutes. Time flies.
You know I suck up at any time you give me. Yes, please, go ahead.
Okay. Dejan Bogdanovic, Juniper Networks. So I actually started working on an autonomic implementation just as a prototype. And what I realized in order to be able to do that from a single agent, I have to cover multiple devices, and that we need something that, at least as a transition, that in order to achieve some of those functionalities, you really have to you cannot expect that every device will have an autonomic function, that you will have sort of a agent domain that will cover multiple devices and that it will know what to do on each device separately. So I didn't have time to put it as a draft for this IETF, but I think this is something we should consider, as a stepping stone to get to the goal.
Absolutely, and that is that's the question. How much do you want to centralize? Because you can have semi-central node that takes care of several others. You can completely distribute it. There are various ways in between, right?
Well, the idea is that they are all in the same geographical, physically, they are very close to each other, essentially on a LAN network, a few of devices that you would concentrate under a single autonomic agent.
Okay.
By the way, just speaking as a co-author, still probably getting off, but we specifically didn't put this in because we didn't want to boil the ocean without having really outside validation that these things are necessary, right? We saw that as well, so it would be great if you want to bring in, that aspect into the reference model.
Yeah, I'll definitely do that because I tried both for microwave and for optical, and I realized it just doesn't work unless you do something like that.
Yeah, speaking with my working chair head, we are actually at the very beginning stage to understand, what the requirements for the autonomic networks. So you are very welcome to, write your specific requirements. Then we will later, maybe form design team to work on, what maybe become the common reference model in this working group. So, got it.
John Strassner, Huawei. I've done a bit of autonomics in the past, so one, I wanted to urge the working group to not just think in terms of APIs, but to think more in terms of software contracts. So if you think of an interface that has additional semantics, for example, pre and post conditions, invariant attributes that do not change over, for example, the life cycle of a method, that rigor and formality, in my experience, has been mandatory to do autonomic or semi-autonomic functions. Second, on capabilities, I'd like to work with you to more formally define capabilities, and I'm not sure that GDNP, I think GDNP might get a little overloaded if it tried to do negotiation for everything, just something to think about. And so third, sure, I'll contribute.
Thanks, John.
Can I just ask a chair question back for the formalisms that you were referring to? Are there any examples from other IETF efforts that you could point to where these formalisms have been embodied?
From IETF efforts, no, but from other SDOs, yes.
Okay, thanks.
So yeah, if you can point us in the right direction, that would be useful. The software contracts.
We cut after Bing. Go ahead.
Bing Liu from Huawei. First, I'm willing to contribute both on the content that haven't been filled in the current draft, or maybe some possible extension. Okay, another is a clarification question. Could you go back to the table of contents slide? Yes. In the section 7, autonomic control plane, there are several items under it. And I think that maybe we should distinguish the concept that the autonomic control plane itself is a component as a autonomic infrastructure. And the things under it might more like autonomic service agent that are running on ACP. They are not part of the ACP component.
Correct. The ASA is not part of the ACP. The ACP is really, see the ACP as its own virtual network. And an autonomic service agent is like a PC, to use a reference, that sits on top of it, right?
Yes. So maybe we can make it clear that these ASA are not part of the
yes.
ACP.
Okay.
Yeah.
Thanks for clarity. Please, there are a lot of people here that hear all of this stuff for the first time. A lot of us have been in this for a long time. So when these things pop up that don't make sense, please alert us. Send us an email. Okay, thanks.
Hi everyone. So in this talk I will introduce some concepts on autonomic functions coordination. Next slide please. So why do we need coordination in the first place? So as you can see on the slide, on the
Sorry? Yeah, get closer.
Okay. As you can see on the slide, you can have two autonomic functions using parameters and metrics in order to operate. The first type of conflict you may encounter is metric value conflict, when a given metric is influenced by the parameters of different autonomic functions. And the second type of conflict you may also see is a parameter value conflict, where a parameter of a function is modified by two different autonomic functions. Next slide, please. The problems become way harder if you consider multiple autonomic functions running at the same time in a network. As you can see in this conflict map, when I say conflict map, for instance, this is a diagram showing interactions among autonomic functions in a 3GPP LTE network. And this is only the static version, things that you get before autonomic functions get deployed. So assessing this interaction is quite complex already, even in a static way. Next slide, please. Beyond just conflict, you can also consider different types of interactions among the autonomic functions. Of course, the conflict are the most important one to consider in the first place, because this is where you will need to solve concrete problems. Otherwise, you will get issues in the operational state of your network. But you can also consider cooperation between autonomic functions. Autonomic functions can help to improve the performance or the behavior of another autonomic functions. You can think about traffic forecasts for a traffic engineering function. And finally, a third type of interactions concern the dependency among the functions, where for certain autonomic functions cannot work properly if another one is not present in a network. And think about service chaining aspect. Next slide, please. So in order to tackle the coordination problem, first approach is to decompose the life cycle of coordination. There are essentially three stages where you can or you need to work on the coordination thing. The first stage is specification time, when you design or specify your autonomic function. At this stage, what you will need to provide is a description of the elements that an autonomic function manipulates. For the metrics, the parameters, type of action it performs. All these elements are really essential for you to build the static map, the thing we have shown on the previous slides, and all the relationships among the autonomic functions. The second stage is when you deploy autonomic functions over the network. And at this stage, you will need, for each instance, it's not only for the general class of function, but for each instance of the functions you will deploy, so basically the agents, the number of agents, and also taking into consideration over which resources they are deployed. And this is the comment that was made by Dean, that you need to make an inventory of all the metrics, but the specific metrics that are monitored, the different actions and parameters that will be modified, and also all the relationship among these metrics and parameters over the network, over the deployed network, I mean the devices and the agents. This will allow you to build a dependency graph among the deployed autonomic functions. And this is based on this dependency graph, the dynamic dependency graph, that you will be able to identify the potential conflicts. And I will show in the next slide an example of this. And this is where you end up having a deployed or dynamic conflict map, which is the element you will need to manipulate in order to arbitrate the conflict. Then the last stage is the runtime. And this is actually the time where you will arbitrate the conflicts among the different loops. And you will use different coordination strategies and different available mechanisms in order to arbitrate those conflicts. But you will also need, at runtime, to be able to infer new dependencies, because the network is dynamic, so you will have new autonomic functions coming and going, managing new devices or new resources. And for that, you will need also to update dynamically your interaction groups, your conflict map. The next slide, please. So the next slide is one approach. It's just to illustrate the concept of the deployment and how you will end up with a dynamic conflict map using the descriptors of the autonomic functions, so the type of metrics, the parameters, and the actions they perform on the network, So I will not go into the detail of that. I can show you some papers that illustrate that, but what you need to understand here, we have a description of what the autonomic functions manipulates, and so you create a graph. Next slide, please. And if you overlaps all the different autonomic functions with all those metrics and parameters, you are able to identify, to construct a dependency graph and identify potential conflicts. So in this graph, they are illustrated with the stars. And this is where you will need to focus your attention to arbitrate the different conflicts. And so the next slide, please. How you will arbitrate these different conflicts that can depend on different coordination strategies. So there are, of course, the approach that an operator may choose to generally address the conflicts in its networks, but there are also the capabilities in terms of mechanism available that are provided in the network, so the different type of algorithm to address the conflict. You can have very simple mechanism or strategies like random or token-based. So this is very basic, and globally this is what is put in place in some networks today. But also the benefits and the level of controllability of the output of this mechanism are also quite limited. Then you can have other approaches like separation in time, where you will, for certain groups of autonomic functions, you will group them in terms of their time scale. A very short range like millisecond or second type of actions versus hours or days for optimization. This is especially what is done in mobile networking for all the LTE SON functions. And then you will address the different conflict groups based on the timescales. You have also hierarchical optimization, which is more a way to set priorities among the different autonomic functions. And for that, you will end up by managing the different priorities among the functions, and it's easily coupled with the separation in time, and also with a policy-based management approach. Then you have other, I would say, more complex, but also maybe sometimes more capable of tackling more complex problems, approaches, which is, for instance, centralized multi-objective optimization. So this type of approach is a bit like having a kind of super algorithm that takes all the inputs, all the outputs of the autonomic functions, and tries to optimize or to deliver the best utility functions out of this set of inputs, outputs, and then retrofits all the settings towards the different autonomic functions in order to really steer the networks towards a convergence point or a specific operational point. It's a bit like being God in a network. And then there are other, again, more complex control theory approaches which can be implemented, but I don't think it's the topic today to go through all of that. But there are many types of algorithms you can imagine, and it also depends on the type of conflict you want to address based on amount of reconfigurability you can afford, the time to converge for the coordination time, etc. So various set of possibilities considering coordination strategies. The next slide, please. So the important point which I would like to discuss today, which are relevant for Anima, are the implication of coordination for autonomic functions. First, coordination, based on our experience, is really a must-have feature if you want to deploy autonomic capabilities in a network, because this is the only way, except very basic configuration, to ensure stability and convergence in your network. It's a function that is cross-autonomic functions, in the sense that, as I shown in the different conflict graph, is that all functions needs to contribute to the coordination mechanism, even by only sending the metrics and parameters they manipulate, because this is how you will be able to have a overall coordination approach. So it must be, at some level, a reusable component, part of the reusable service that Michael was presenting.
I'll wait to the end.
It's the last slide and just the three last points. Also, at some level, in order to perform an efficient coordination, you will need to describe, or you will need common descriptors and at least a description of a common life cycle. if you register the different autonomic functions, or if you discover them, you discover their capabilities, how you negotiate and what you negotiate. So you need to have come to some consensus on what is in the descriptors and the different stages of the life cycle of the autonomic functions. But also, and this depends on how far you want to go on the capabilities of the coordination mechanism themselves. But you need to have also a way to represent information, or maybe even knowledge. This is especially essential if you want to be able to build a more advanced conflict map. I understand that this is very opening a Pandora box here, but this is very important for such a functionality. And of course, as was presented by Michael at the beginning, that all the aspect of interfacing between this utility function and the other ASA in the approach, how to interface for just having this control or command interface towards the autonomic functions so that the coordination decision can be applied by the autonomic function. So this is a set of open issues. I think we have a bit of time to discuss them right now, and if you are willing, can discuss also by email or by drafts. Thank you.
Yeah, Thomas Eckert. So, you know, I got the feeling that I want this, but then on the other hand, this is, let me say, abstraction and terminology, rich representation of high-level concept where I have a hard time following, right? So it would really be great to have, you know, the most silly, stupid, simple use case example where the most simple, you know, subset of this functionality could be applied to, right? With that description, I think it would be much easier for me to grasp what it ultimately would mean in the components, right? So I've got 3 agents, and they're trying to agree on what is the most simple example.
Okay, I can give you one, but if we go towards 2 simpler examples, then the need for coordination vanish. But just an example is, consider an agent that do load balancing, trying to have, for instance, the best traffic distribution among different links, and another agent which do energy saving, which try to shut down some links in order to save energy. And if you put them both on a router, for instance, you will have one function that tries to shut down links, because for him, the optimization is to save energy. And on the other side, you will have the other agent that will say, I want to switch on links because I want to be able to distribute traffic over additional links. And you will have oscillation between both. So in this case, it's quite easy to arbitrate because you can put hierarchy, and even with a simple policy, you can address that. But then if you add a third agent, for instance, that change something, or for instance, in mobile networks, where you have tens of different agents working concurrently on the base station, this is you end up with the conflict graph that I have shown at the beginning, and this you cannot handle with just 2x2 use cases. But I understand your point, and we may document that also.
Yeah, Brian, we cut off 9 after Bing again.
So this is a rule? Is this a rule? It's always after Bing? So this is Brian Carpenter. I have no difficulty understanding this is a problem, actually. It worries me. I'm trying to extract from it what we have to do in the basic infrastructure components. So my question is, are you actually saying that there is a need for direct dialogue between 2 autonomous service agents which are not supposedly managing the same thing at the, you know, that they have 2 different purposes? They would be in a simple situation, they would be designed and implemented completely independently of each other, but because of the conflict, they need to communicate directly between the 2.
Yeah, I think this is exactly the question we need to answer with this group to investigate, because in past work I have done, we have made some choices, and we have an external coordination agent that tries to get the view and then send the different approach to the nodes, but they behave on their own. You can have different models to address that.
Yeah, I understand that, but the baseline requirement is there is communication not just up and down in Michael's diagram, but also horizontally between the service agents.
Yes.
Okay, thank you.
Many questions were already asked by Turles and by Brian, by the way, very interesting. One of the questions that is not clear to me, does this mean, for a lot of this happens on the ASA level, right? Does that mean the infrastructure needs something that we haven't thought about it? Is there something missing?
I don't know yet because
the ASAV tool later, right? So this is, we have time for that. But if we need something in infrastructure, we need to know this pretty soon, I think.
I mean, it depends how you define infrastructure, because for me, the coordination is something you cannot avoid. Otherwise, you will have problems when you deploy multiple functions. The thing is, you can see it as an ASA that all other ASA will communicate with, and then it's one way to solve the problem. Or you can say it's kind of utility ASA that you put in the infrastructure, like for negotiation, and you say, I need an API or an interface to communicate with that, and it's a general services I can subscribe. I don't know if after that maybe it's implementation choices or deployment model choices. It's something we need to work out on the mailing list maybe, or with some drawings.
Yeah, that's sorry, yeah. That's exactly what we get, some confused here, whether this is only, a zero to, apply on for the autonomic service agent, or it's some, reusable components we need there to support every autonomic services agent. That's different. And for now, our charter, we want to working on the reusable components. So, we know that coordination is important and there are conflicts, but you need to come back with very concrete idea, what's the reusable functions we want in the, infrastructure to be able to support maybe all kinds of coordination. Yeah.
Yeah, understand. Thank you.
Yeah. You want to ask one?
So I've done a lot of work in representation of information and knowledge. I think that this might be one thing that needs to be explicitly added to the infrastructure. I think it's an infrastructural service that the agents would use. I also think that just having a, quote, information model with a bunch of data models is not sufficient. I think that you need some way to reason about knowledge, or else I could have two different capabilities that on the surface appear to be the same, but when you actually look at their dependencies and side effects and blah, 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 they aren't actually compatible. And so for that, you need some type of first-order logic and ontological service. I'd suggest that you take a look at either Common Logic or KIF, the knowledge interchange format. Common Logic succeeds KIF as one way to think about how to interchange knowledge, and I'd be happy to help you.
Okay, thank you, John. Yeah, we'll do that.
Thank you.
Thank you.
Tony?
My name is Mehmet Toy with Comcast, and actually this is my first presentation in this forum. I appreciate for the chairs for inviting me. The real topic is the self-managed network with the fault-managed hierarchy, and it is actually looking the self-managed concept from the fault management perspective. Next slide, please. Next, please. So the problem is this. If you look at today in the industry, the network operators and networks service providers basically monitor the network, and if there's a failure, they can try to fix the problem remotely by maybe downloading a configuration file, mostly. And if they cannot, they basically send the people to fix the problem in the field. Now, I do believe this has to change. So in other words, the network has to be able to find its own problems, fix its own problems, and inform the related entities accordingly. Next slide, please. So in this work, I'm basically proposing a intelligent network element architecture, intelligent network management system architecture, and also a overall architecture for self-managing the networks, and also an in-band communication mechanism between the network elements, network management systems, basically to communicate the failures, communicate the fixes, and so on and so forth. So I'm not proposing any kind of control plane. I'm not proposing any kind of coordination between the agents and things like that. Next slide, please. So I basically focus on the fault management because in the industry today, we actually do automatically provision the CPEs. And we really have the processes. We can do the not only CPEs, but the rest of the network elements as well. So I thought that the problem itself, without going through various avenues, problems is a manageable problem from the configuration perspective. Therefore, I kind of excluded that. Next slide, please. So the first one is a intelligent network element. What is an intelligent network element? Intelligent network element is, first of all, has to be able to self-check periodically and be able to run diagnostics to subcomponents and identify the failures, isolate the problems in the subcomponents. And if that's not possible, then they will be able to go a subset of the subcomponents and run diagnostics, identify the problems, and at the end, if it cannot identify the problem and says, or if it identifies, says, I cannot fix the problem, then communicate to a next level, which is the network management system. Next slide, please. So if you look at the architecture, it is a very high level. As you can see, you have subcomponents. It's called the intelligent smallest replaceable unit. So in other words, if I take a chip on a line card, that is a intelligent replaceable unit from my perspective. So maybe you can combine them, you end up with a subset of subcomponents. For example, let's say if I am doing the deep packet inspection, I may have multiple components contributing to deep packet inspection. I may actually, after running the diagnostics for those subcomponents, I may run a diagnostics to a set of subcomponents associated, providing that deep packet inspection, for example, to see if there is an issue with those modules or not. So then, of course, on top of that, you have a hierarchical diagnostics and trouble identification logic in the network element. Next slide, please. So that's one architecture. The other one is the network management system or operating support system. And that is also has to be able to periodic self-checking capability and also redundant. And on top of that, be able to store the software modules and specific to the network elements, and also be able to verify if network element says the problem doesn't belong to me, it has to be able to verify that's the case, and also able to periodically monitor the remaining components of the network. In other words, you have the network elements, you have the links and other components. The network management system should be able to monitor those as well. Next slide, please. So if you look at the architecture, you have self-checking components, self-diagnostic components, and then you have the network level monitoring diagnostic components, and also the copies of the intelligent network element software. And of course, at the end, again, you have the hierarchical network level diagnostic and trouble identification logic. Next slide, please. So if we look at the self-managing network elements, so now I am switching the terminology from intelligent network element to self-managed network element. And the reason I'm doing that now, I am adding agents to the intelligent network element. So those agents are application, the hardware, capacity, and also operating system agents. So each of these agents basically monitor their own entities and identify the problems, fixes, and so on and so forth. Next slide, please. Next slide, please. This is a very high level what the agent architecture is. As you can see, there is various rule-based logics and also various schedulers and so on and so forth, and also APIs to be able to be interfaced to the various software and hardware modules. Next slide, please. Next slide, please. So if we look at the architecture of a self-managed network element, it has the intelligent network element, as you can see, and then on top of that you have the backup copies of the current configuration files in the network elements, and on top of that we have the intelligent agents, as you can see, the hardware agent, application agent, the capacity agent, and I guess I forgot the rest of the other ones. So next slide, please. So now if you look at the self-network management system, that is being able to again collect the information at the connection level and also measurement and the network element level, capacity measurement and so forth, and store them and initiate and perform the remote fixes on the network elements, and also fix network level issues if there are issues with the network level. Also perform various like connection admission controls, load balancing, these kind of algorithms perform at the network level, and also fix the problems, and as we will discuss later on, also tell the rest of the community how long it's going to take to fix it, and so on and so forth. Next slide, please. So this is the self-managing network management system, and again, the only addition here is now we have copies of the agents. That agents we had in the network element, I also have the copies in the network management system to make sure if something goes wrong, I'll be able to download them. Next slide, please. So this one is now combining the intelligent network management system and on top of the various components for the self-managing network management system, which is the GUIs, the fix manager for each network element types, traffic management, algorithms, and so on and so forth. Next slide, please. Next slide, please. So what I have described you very high level so far is the intelligent network element, intelligent network management system, self-managing network element, and also self-managing network management system architectures. Do you want me to continue, finish it, or should we take the question? I don't know which one you prefer.
I have a quick question. Bhumi Khashnavish, have you implemented it in Comcast network?
I love to, but you see the problems. Yeah. Problem is with the not having vendors be able to support this yet.
Okay. My second question is, if some of the self-diagnosis and testing, start in many network components at the same time, it can bring down certain segment of the network. There is some danger with that.
Why?
Because if you are doing the testing, some of the components may not be available for service.
You can run in the background. We always run the testing in the background. You can run the, we do, if you just take a network connection, for example, we run the keep availability, keep alive messages in parallel to the normal traffic. You can do the same thing in the network elements as well. Of course, depends on what you do. I mean,
so there are some reports, publicly available. This kind of things causes outage. So I can send you offline. So some of the informations are there about that. Thank you.
So if you look at the centralized architecture here, the idea is self-managing CPE, and of course the self-managing edge routers and the backbone routers, and now all of them is connected to a centralized network management system, and they communicate with the same protocols that we have today. I'm not asking for anything new in terms of protocols that the NMS communicate with the rest of the network. Next slide, please. So this one is a distributed network architecture, which is...
Can you try to wrap up in 5 minutes?
Okay.
Thank you.
The other speaker used 35 minutes, so I just want you to know that. Over here, you will have the network management system for each regional area, and then each regional network management system will be responsible from the basically monitoring, isolating, and fixing problems in their own region. If they cannot fix it, actually they again communicate with the centralized network management system. Next slide, please. So let's move. Next slide, please. Okay. I use the similar concept actually for the virtual networks. So in this diagram I have various physical networks. Now on top of that I have virtual networks, like virtual network 1 and 2. Next slide, please. So now for the virtual networks, I am basically allocating 2 agents, one for applications, the other for the capacity management. And then we will have a NMS only dealing with the virtual components. It is possible that we still use the same NMS, which really deals with the virtual components, but as well as with the physical layers as well. Next slide, please. And this is the, if you have, next slide, please. So you can have actually the distributed as well as a centralized approach in the virtual networks as well. Next slide, please. And so this is the distributed version of the virtual networks. Again, you will have basically end up with the regional virtual network managers. Next slide, please. And this is the architecture for the network element. If you have the virtualized components, which really nothing more than adding the agents for the virtualized networks. Next slide, please. Next slide, please. So this is a similar concept for the SDN. In the SDN, as you know, it's an application layer, control layer, and infrastructure layer. If you go to the next slide, please. So I again assign agents for the application layer and as well as for the control plane. So therefore now you can deal with the issues in the application level, application plane as well as in the control plane. Next slide, please. 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 Okay. So I skipped those. Now I want to jump into the in-band communications. The idea over here is this. Number one is I would like to have one common message format for all the failures and for all fault management communications. As you know, we have loss of signals, AIS, RDI, and so on and so forth. These are different format, and also they do not actually provide the information that we want. So what I would like to see is one single format and carry all the information that we want. So for that is, next slide, please. So in addition to the operational state, failure types, what failed, what not failed, and also I would like to see the fixed time. So in other words, if something goes wrong in one of the network elements, I would like to see the network element to say, this is going to take this long to fix it. And this is very, very important concept for the service operators, so I know how long my service is going to be done. Next slide, please. So,
I mean, you have 1 more minute.
Okay. So over here, basically, I have described I took an Ethernet format and tried to describe what additional fields that I can add to provide the communications. As you can see, I identified the failed element. I identified basically what is failed and who's going to fix it and how long it's going to take and so on and so forth. Next slide, please. So this one just shows what the hierarchy is. As you can see at the top, let's say if I have a failure in the network element, then the network element itself checks whether it can fix it or not. It says if it cannot fix it, then send a message to the NMS, and NMS basically try to do fixing and then send message to everybody else to say this is how long it's going to take. And if it can fix it, then it will basically, if the NMS cannot fix it, then it will come to say, I will send a message to the field technician. So field technician basically looks at say this is how long it's going to take and send messages to everybody else. Thank you very much.
Yeah, thank you very much as well. So I mean, this is a lot of stuff, and I'd say if everything like this gets finally implemented, we've got OEM advanced for a decade, and all of that in 15 minutes. So I agree on the challenge. Unfortunately, we've run out of time, so it would be great if we can take the discussion about this directly to the mailing list. And Laurent, you're up.
I'll try to be short. Okay, thank you. Second talk, this one is not on the coordination, it's on the capability for trying to anticipate on future network condition and use that for specific actions for proactive management in the network. Next slide, please. A brief history. So this concept and mechanism have been already presented at Energy in London, and also as a use case in the UK and both in Toronto. Today, the question will be more what will be the remaining path to make towards an Anima compliant ASA for this mechanism. Next slide, please. So how the mechanism is working very briefly. So the first step is to connect and collect different data or information sources. It can be on the device or it can be on other repository. The second step inside the mechanism is to compute a near real-time risk analysis or risk prediction. Next slide, please. Okay, no, sorry, previous slide. So there is an issue on the slide, but that's...
So, okay, so you want the...
If you have the PowerPoint, it will be...
There is not more on the slide, we're afraid.
Maybe... No, there's no more on the slide. That's a PowerPoint.
Okay, try. Okay, thanks, that's all. Thank you. Okay, so, and the first step, as soon as we have a risk level, we may trigger different types of actions. So here I just illustrated three applicability we have tried in our lab, using the risk level to steer traffic using IGP over non-risky links, to adapt the level of recovery for MPLS LSPs, or to adapt the timer detection for SPF. But we can imagine other type of actions. And then a fourth step could be based on the result of these actions. Next slide, please. Yes. Feedback from the different actions, but also feedback from the sensing we have from the network, to learn about the performance of the risk estimation and the result of the action. Next slide, please. Some remark on the mechanism. So the learning, of course, will be to improve both the accuracy but also the utility over time of the mechanism. We may think about pure local mode, where all the decision will be based on a local agent, local decision, but also local measurement of the information or the monitoring of the device. So this can be really without any connection to the outside of the device, and still have a distributed execution using, for instance, OSPF to convey the messages. We can have also more global approach where this can be used, for instance, to mitigate local instabilities, but also to get a deeper risk understanding by using a correlation or a sort of awareness about the context at the network level. And also, further benefits will be to be able to have a local and global risk information or patterns that can benefit to other mechanism for their performance. Another point is, as I mentioned, for the type of action we may imagine is the time window for the risk prediction. If we have a big enough time window, we can be in a class of actions which I call preventive maintenance. So if you have hours, you can even send a field technician, for instance, to change a card or to change a battery or something that has failed on a device. If the time window is way more shorter, like seconds, minutes, or even below seconds, you will be in a class of action which is more towards automatic mechanisms such as IGP mechanism or protection restoration, activation of cold standby, etc. Next slide, please. As what presented previously, just next slide, it will show something. I've tried just to make a tentative mapping of the different components of this mechanism on the reference model that was in the Energy draft. So we have the aspect of sensing the information from the networks or for the standard operating system of the device. the module that will assess a risk and disseminate this risk towards the risk-aware mechanism, so that this can be different types. From the intent, you will have the different fault management strategy or strategy of the mechanism, and also interaction with other risk-aware mechanism that can go via other agents. Next slide, please. And this is a discussion I would like to have for Anima today. Is really a question of how to be compliant and what will be the impact towards Anima specification for such a mechanism. I'm not pushing at all. I know that it's not the mandate currently of Anima to specify agents or to be at that level of specification, but it's just to show that how do we draw the line between what could be a common component from what will be a specific, remain specific to ASAs. Here, what I'm presenting is an ability to anticipate future network conditions, which may be a new capability of interest to many other mechanisms. The question is how to make it accessible and useful for other ASAs. Is it a common component? What is his place in the reference model? What are the interfaces we need to cater for this functionality? Also, we can design a very specific mechanism, like what we have implemented is really specific, for instance, for SPF or for MPLS. But the base thing is that you can make it very generic, like assess a risk or whatever, based on what you estimate. But you can make it customizable by the intent or by the capability of the network you have in front of you, and so not replicate this functionality for every agent. But the question also raised is we need at some point common ways to connect to information sources. If we need to be able to assess a good quality of risk, we need to have information either from the device or for other sources of information. How we connect to that in a common way. The same apply for dissemination of this risk information to the target mechanism. For that, we can, of course, reuse some of the infrastructure components and also the discovery to discover what are the counterparts of this mechanism. Common ways to learn and to build knowledge, but that's not enough. It's also ability to store, to query, to process information in order to extract higher level information. And of course, my question will be to what kind of interfaces to GDMP, and do we need to specify a specific GDMP objective for such a kind of risk or a predictive risk functionality? Okay, but this is really, I mean, open point is just to raise the discussion here or in the mailing list to bring forward the work of Anima as an example.
Thank you very much. To stand up just as an individual contributor. So this last slide is interesting because I think it points to what is close to what we need to do as milestones. First, validate that the infrastructure has the necessary requirements or functionalities to support agents. Now, if I look at this, it doesn't seem as if there would be any difference in this list whether you're doing the proactive use cases that you are interested in, or if I correctly interpret what your previous talker was saying from Comcast, maybe reactive ones, right? Detecting failures and then correcting them, right? I mean, so if there basically is a way to create this type of prioritized list of requirements against the underlying infrastructure, what it should provide kind of from that list, right? Especially if it's clear that it's necessary across multiple agents, I think that would be a really good way to vet that the ANI is complete, or at least complete enough to declare a partial success and then do the next set.
I agree. I think there are a lot of common between both reactive and proactive mechanism, especially for fault management. Mm-hmm. And we may really focus on this specific commonalities instead of specific the things that are too specific that can remain in the agents.
Yeah, Brian Carpenter, thanks for that. That was actually very interesting. And although this use case is not on our list of deliverables, I think it's very useful for our list of deliverables that this sort of mapping is going on in the background. So we can test our ideas as we go. And I would actually make the same remark about the previous presentation, except that I wish we had had the previous presentation in abbreviated form
in the UCAN BOF because, you know, maybe it's, I can't tell by looking at 43 slides, but maybe it throws up some requirements that we weren't aware of during that BOF. So I'm actually going to, if I may, suggest that the Comcast case should be reduced to 5 slides in the format that we used in the UCAN BOF, because that was designed specifically to extract requirements for the infrastructure. And I think that will actually be a very useful exercise for Comcast. Producing 5 slides surely only takes 5 minutes.
Bin Liu, could you go back 1 slide? As described in current reference model draft, this autonomic model is mostly within one autonomic node. So for your case, such as a risk aware mechanism or assessment mechanism, is it sufficient that only within one autonomic node, or there needs some interactions between different autonomic nodes?
Yeah. Can you go back just the nodes one that's here? We can have different modes of operations. You can have a fully local one, which this is one we have implemented. You monitor, for instance, the CPU information or memory information that you have on Linux OS. And from that, you can extract some risk level. Or it can even be a mock-up. And then, based on this information, you can derive a risk at this device level, and then just use the local OSPF instance to change the link matrix, and then this node can either appear or disappear from the topology based on very local, local decision. And so this is one mode of working, and you can replicate it. I mean, it can be distributed. It's not only one node; it can be in all the nodes. Then the global one is more a network approach, network-wide approach. Then this is not what we have studied so far. There are other considerations for communicating among the different agents. What do you communicate? How do you get a network or global risk information or patterns? What does it mean? And how do you use that in an efficient way?
Okay, thank you.
One comment for you and also for previous speaker. You know, for those work items we haven't explored before in the Anima working group, that would be very helpful if you first come with, you know, requirements rather than design solutions at the very beginning. You know, we need to understand the requirements. Afterwards, we can, you know whether we really need that or not, whether, you know, the working group takes that as a milestone or a future solution. Yeah? Thank you.
I agree. Thank you.
So we will have the chair closing. We'll do that?
Mm-hmm. Sure. Yeah. So I think that was a busy week, and so I think we made good progress on, you know, also outside all the presentations. One of the conclusions that we reached for the milestones is that we would like to start working on design teams for the bootstrap and the signaling milestones. So if you're interested in either of these areas, if you can please send an email to the chairs. We'll also reach out individually to the folks we would love to have on those design teams. And the idea is for these 2 building blocks to create really, you know, a common design going forward for each of them, and not, you know, beating heads up on 5 individual submissions. So I'd hope that, you know, when you put in your name that you're clear with that goal. We don't think that at this point in time we need some design team for the autonomic control plane, because there doesn't seem to be, you know, any outside work beside Anima that is colliding, overlapping with it. So we've seen very little contention. But the ACP, of course, has dependencies against the bootstrap and the signaling. And so we'll definitely want to make sure that in the design teams of those 2 components, the requirements for the ACP are well understood and taken care of. We think that the bootstrap is the most urgent one, because there is a lot of, you know, good discussion, ongoing parallel work in NetConf, and having talked to working group chairs and other IoT groups, there might even be more potential parallel work that we might even be able to avoid and instead bring into Anima if we act now. So that's basically we want to get started, and we also want to set up an interim virtual meeting for that bootstrap design team and start working on that. So from the working group chair side, beside coordinating that, I think what we would like to do is to see how we can provide questions that, if answered through the design team, should hopefully bring us to make progress on the actual milestone targets, right? So primarily things like the scenarios that we want to understand to be in scope and get resolved as part, for example, of the bootstrap, and then even more so how the individual building blocks of the milestone components that we've talked about should interoperate with each other so that the mutual requirements to finalize the protocols are well understood. So that's kind of the plan. And once we see that we're making some progress with the bootstrap and hopefully the interaction with the signaling and the ACP, I think we can take back that work into the reference model. And basically, I don't think we need to start driving the reference model independent of first making progress with these three components. And more from your side?
Just one more. When you contact the chairs for your willingness to join the design teams, please also, provide which time zone you are. That's very important to coordination globally. We are all in different time zones. If people unfortunately cannot reach very convenient time for everybody, then we have to spare the pain by set up two meeting times and switch between them for two meetings like that. So please give your time zones that's where the chairs can set up the most suitable time for the meetings. Thank you.
Yeah. Okay, thank you very much for being here. Hope we'll see each other either virtually or if not in Prague then. Thank you.
Thank you. I guess we too should set up a meeting next time, next week, sometime Tuesday.
So what is it? When it is evening for you, your
where will you be?
Just a second, yeah, I'll need to get to the airport quickly, so just a second. Okay, what's up?
Was my presentation okay, or did I? That's okay. That's okay.